Hi guys, this is Mr. Mellor. This is a quick lab help video for lab number 4, quarters and vectors. Alright, let's go ahead and get started. So the concept that we're talking about in this lab is this idea that 2D motion can be broken up into two sets of 1D motion. And so what we're talking about is, if you remember from class, we threw an object, at least some of us did, and we shouted Kobe just like middle schoolers enjoy doing. And so what we can see that hopefully what we can agree is that when you put an object in projectile motion, which is, it's really two-dimensional motion, okay? And so we take an object moving in two-dimensional motions and we treat its overall motion as being made up of a horizontal component of its velocity and a vertical component, okay? And so if we throw an object, the path the object would take might be shown like this as a diagonal, and that would be, we could break that up into a horizontal component, motion left to right, because we know, say, if we throw a ball, it's going further away from us, and then a vertical component, which we know is up and down. If we throw an object, because as we talked about free fall previously, we know that that object is going to initially go up and gravity is going to pull it downwards. So when we talk about projectile motion and throwing objects, we're really talking about two-dimensional motion, which is very close to how things are actually moving in the real world. And as a result, in order to simplify things, we break it down into two sets of one-dimensional motion, which is a horizontal component and a vertical component. Okay, so we're treating horizontal and vertical motion as completely separate, and that's what we're testing in this lab. All right, so with the same idea, if we have, because horizontal motion and vertical motion is completely separate, gravity is just a vertical force, okay? And so if you were to drop an object, we know from experience and some practice, because we practiced free fall problems previously, that gravity is going to cause an object that's falling to pick up speed, okay? And so because the object that's falling is moving vertically, gravity will act on that vertical, because gravity acts up and down vertically, it will cause that object to pick up speed. And remember, we have the acceleration to gravity, the rate at which an object changes speed every second, which is 10 meters per second, 10 meters per second squared. So if you drop an object, it's going to pick up speed. The acceleration to gravity is pointing downwards. The object's velocity is pointing downwards, and so when the velocity and the acceleration are pointing in the same direction, you get the object will pick up speed. Okay, so if we have vertical motion, that will be affected by vertical forces. The opposite, but what if we have horizontal forces? Well, we said if we rolled an object along a table and we took a picture of the object every second, we would see that our object, provided it's moving with constant velocity, would have the same distance between every second. It moves the same amount every second. And so it has the force of gravity acting on it, because we know that just like you were sitting in your chair watching this video, we have gravity pulling down on it, but it's that gravity, which is a vertical force, is not affecting the horizontal motion of the object. The object's not accelerating left or right. It's not picking up speed, decreasing speed because of gravity. And the reason why is because vertical forces, which cause acceleration, because remember, forces are a push or a pull, and pushes or pulls cause things to change motion, cause them to accelerate. Because gravity is vertical, it's not going to affect horizontal movement. Okay, so the purpose of this lab, we're knocking some quarters off of a table, is to see that horizontal velocity is not affected by a vertical acceleration, which is the result of a vertical force. Okay, so the instructions for this is you are going to set one quarter on the edge of a table, then you're going to take a second quarter, quarter B, and you're going to slide it at the first quarter. And so what you should see is the quarters will roughly leave the table at the same time, so very closely to the same, because the quarters are pretty small. But the first quarter that was on the edge of the table is going to be knocked off with a horizontal velocity, and the second quarter is going to fall off with less of a horizontal velocity, and ideally not very much at all, such that it really only has a vertical component to its velocity. However, when they're leaving the table, neither of the quarters is going to have a vertical velocity to start with. So it'd be just like dropping it from rest. Neither has a vertical velocity, but quarter A in our ideal scenario would have a horizontal velocity. So we're going to see how that affects things. What we should see is that regardless of what the horizontal velocity is, they should hit the ground at the same time. Why? Because the only thing that affects vertical velocity is gravity, and the vertical velocity is what determines how long it takes to hit the ground, okay, to move in the vertical direction, which is to traverse our height from the height of our table to ground level. All right, so let's go ahead and take a look. So this is the setup. All you do is you take two quarters and you go ahead and hit one into the other off of the table. All right, so this is in slow motion, it's not lagging. Okay, so it's a little bit hard to see, but you should see that they approximately hit the ground at the same time, even though coin A has a greater velocity, greater horizontal velocity than coin B. It doesn't matter because initially they both have a 0 vertical velocity, and that 0 vertical velocity is the only thing that matters when our object is moving up and down, okay? And we're going to get more practice with this. All right, so there's a second trial. Moving our coin, again, it's in slow motion, it's not lagging. Okay, so now we have two coins hit. All right, so clearly coin A hit the ground first in this time. And so why is that the case? Well, this is the issue with our experimental setup. So as we had our one coin, coin B, it hit coin A and a second coin, we'll call it coin C, and as a result, there was a lag in the amount of time it took for coin B and C to leave the table, whereas coin A was immediately knocked off. And so you can think that coin A started at its initial vertical velocity of 0 sooner than coins B and C start at their initial vertical velocity of 0. Okay, and so why are we specifying vertical velocity of 0? Well, that just goes back to our free fall problem, which we remember if you drop an object from rest, the acceleration due to gravity is going to cause it to pick up speed at 10 meters per second every second. Okay, and so just like our example where you're at the beach and you want to impress your friend who you just met, some attractive stranger, and they're wondering how tall the cliff is, you drop an object and you count out 1, 2, 3, 4, and if t equals 5 seconds, you hear it hit the ground, and you know that that is in fact when that time you can use to calculate the overall height of the cliff using our equation. Distance is equal to 1/2 times the acceleration of gravity times time squared. D equals 1/2 gt squared. Okay, and so in this case, because we started at a coin A started at got off of the table first, it had a little bit more time to accelerate. And remember that time for things to fall, it takes a very short amount of time for things to fall. When I climbed to the top of my house, which is 30 feet up, and dropped an object, it only took about 0.75 seconds for that object to hit the ground. So any incremental change in the amount of time objects have to free fall, that can show up as a large distance traveled. So that's why we saw, even though what we had here was our setup was not ideal, and coin A definitely hit the ground first. All right, let's see trial 3. All right, so this one is much closer. And so when you saw that the two coins were leaving the table, they left the table at roughly the same time. Coin A had a greater initial horizontal velocity, and its horizontal velocity stayed the same the entire time because there's no horizontal force acting on the object. The only force acting on the object when it leaves the table is the force of gravity pulling it downwards, which is completely vertical. And so we know a force causes an acceleration. An acceleration is the change in velocity over time. And so a vertical force can only cause a vertical acceleration. Horizontal velocity is not changed whatsoever. So it makes no difference whether or not object A is going faster horizontally than object B. As long as they both left the table at the same time, approximately they're going to hit the ground at the same time, because what matters is the vertical velocity. All right, so let's take a look at our lab. So this is what ideally we should have seen in our scenario. Coin B running into coin A, and we see that coin A has a horizontal component to its velocity. That's why it's getting further and further to the right in this problem, and coin B is roughly falling straight down. Here's one thing to notice from this diagram. You should be able to see that each time point represented here, they're both at the same vertical height, and that's very intentional, because as we drop them, we start off with initial vertical velocity of 0. 1 second later, they're at a instantaneous vertical velocity of 10 meters per second. Another second after that, they're at 20 meters per second, 30 meters per second, 40 meters per second. And so they vertically have traveled the same distance because their same vertical velocity initially was 0 when they left the table. But why isn't it moved left or right? Because B doesn't have, in this ideal scenario, B does not have a horizontal velocity. Only A does. Okay? So let's go ahead and take a look. Okay, we're going to write down our qualitative observations. I'm not going to fill these out entirely. You are welcome to look. So I'm only going to fill out the first one, or the second one, which we discussed in the video. Coin A hits the ground first. This is due to experimental error, setup error. Okay, and the other two, please fill out yourself. I strongly encourage you, and of course for the lab, you're required to do this activity yourself. All right, question 1. Draw the horizontal and vertical components of the velocity vector of each coin on the image below. Use either of the arrow objects or the draw feature in Microsoft Word. Okay, so we've started doing this for you. Remember in class, together we drew the arrows of an object drawing in free fall going vertically. Remember that arrows represent magnitude and direction of the velocity vector. And so, as we know, if we drop an object in free fall, its velocity picks up speed every second. That's acceleration due to gravity we talked about. Oprah's a huge fan of acceleration due to gravity, so she screams it out. You get 10 meters per second squared acceleration. And so at each second, the arrow should get bigger and bigger. So let's go ahead and do that for B. All right, so at t equals 3 seconds, our arrow should be larger than these two. At t equals 4 seconds, the arrow should be even larger. And at t equals 5, the arrow should be the biggest yet. Okay, and so I use the draw feature here at the top. If you go to the home, and then you should have draw feature here. If you don't have draw feature, you could use insert, shape, and use one of these arrows right here. Okay, so no obstacle for being able to draw in Microsoft Word. Next thing you're going to do, so we're treating horizontal velocity and vertical velocity as separate. Well, we've gone ahead and we've already drawn the vertical velocities here. And so one thing to know, because in this ideal scenario, coin A and coin B have left the table at the same time, at t equals 0, they have the same vertical velocity, which is 0. 1 second later, they're going to have the same vertical velocity, which is 10 meters per second pointing downwards. And at t equals 3, they're going to have the same vertical velocity pointing downwards. And t equals 4, they're going to have the same vertical velocity as each other. Okay, so we've already solved what the vertical velocity should be. Let's go ahead and just make sure that we're going to draw that component of A right now. Okay, so what we're doing is we're making sure they match in length with coin B over here. Why should they match in length? Well, we're making sure that they are, and so here we actually have a little bit of arrow. If we want to make them match in length, this diagonal arrow should be a little bit longer. Okay, but why should they be the same length as B? Well, we have the same force of gravity acting on both the objects, and as a result, the acceleration they experience in the vertical direction is the same. And so if they've left the table at the same time, they both started at initial velocity of 0 in the vertical direction, then they should pick up speed at the same rate. And so at each instantaneous second, they should have the same vertical velocity. Okay, so we're going to show that by drawing an arrow downwards. So that's the arrow we just had right there. So what about the horizontal velocity? Well, remember we said that horizontal velocities are only affected by forces that act in the horizontal direction. We know that's not the case for gravity, which is our only force here. So there's no acceleration in the horizontal direction because there's no force. And so what that means is if there's no acceleration, remember acceleration is the change in velocity over time. If there's no acceleration, that means our velocity is going to be constant. And so a constant velocity means a non-changing velocity. So the horizontal component of our velocity needs to stay the same. Okay, so that means our horizontal arrow needs to be the same length and the same direction for each one. So we're going to go ahead and draw the arrow as the same length and the same direction. Okay, and on your lab, please put this in red and blue to specify vertical velocity versus horizontal velocity. Okay, so our takeaway from this is we separate 2D motion into two sets of 1D motion, a horizontal velocity and a vertical velocity. Together they create our overall motion, which would be movement in a diagonal. All right, let's see. Question 2, highlight your answer. Once coin 2 has left the table, does its horizontal velocity ever change in magnitude? I'm not going to circle the answer here. I'm just going to tell you. So its horizontal velocity never changes in magnitude. The answer is no, because there is no horizontal force. There's no horizontal acceleration as a result of the fact that there's no horizontal force acting on the object. Okay, so its horizontal velocity is constant. The answer is no, it does not change. All right, now question 3. Explain your reasoning to question 2. All right, your answer should include acceleration due to gravity. Well, the acceleration due to gravity acts vertically, so G is vertical, moves down, V horizontal is moving horizontally. And so the horizontal velocity is not affected by vertical velocity. They're completely separate. And so the acceleration due to gravity is a vertical acceleration. To change a horizontal velocity, you need a horizontal acceleration, which is not provided by gravity. So the answer is it stays constant because the acceleration due to gravity acts downwards, and our object or horizontal velocity is acting in the horizontal direction. All right, so why should both quarters hit the ground theoretically at the same time? Well, our answer to that is simply they should hit the ground at the same time because ideally they've left the table at the same time. And so that's the issue with the experimental setup. But if they've left the table at the same time, it would be like dropping them in free fall, letting them go at the exact same time. So at the split instant, they're at t equals 0. They have a vertical velocity of 0. Even if it has a horizontal velocity, we don't care about the horizontal velocity in terms of how long it takes to hit the ground. We only care about the vertical velocity, which is the speed in the downwards direction. We don't care if it's going left or right, because we only want to know how long it takes to go downwards to hit the ground, right? So how long it takes to go down to hit the ground, that's purely dependent on its vertical velocity. And in this case, our vertical velocity for both quarters is going to be the same as long as they get off the table at the same time. Even if one has a horizontal velocity and one doesn't, one has a greater horizontal velocity than the other, that doesn't matter. The vertical velocity is the only thing that matters here. Okay, so same vertical velocity. Okay, so that's the end of our lab help video. I apologize, it's a little bit long. You're welcome to watch it on 2 times speed as usual. I hope that, well, we're going to continue to get practice with this in class, and I will see you tomorrow.